On the morning of August 23, 1991, a $180 million concrete structure the size of a city block was being slowly lowered into a Norwegian fjord. It had taken 3 years to build. It weighed over 40,000 tons, and in a matter of minutes, it would be gone. The men on board heard a sound first, a deep rumble from somewhere below. Then came the water. Not a trickle, a flood. Within 3 minutes, the platform was sinking at a meter per second. The crew abandoned ship. As the structure plunged into 220 meters of water, its concrete chambers imploded one by one, each explosion sending a shock wave through the fjord, strong enough to register as a 3.0 earthquake. By the time it hit the bottom, there was nothing left but rubble. The total loss, $700 million, at one of the most expensive engineering failures in history. And the cause? A number that was slightly wrong. To understand what happened, you need to understand what Sleipner A was, and why it mattered. The North Sea in the late 1980s was one of the most important energy frontiers in the world. Beneath hundreds of meters of freezing, storm-battered water sat enormous reserves of oil and natural gas. Extracting it required engineering that pushed the limits of what concrete and steel could do. Norway had developed a solution called the Condeep platform, short for concrete deep water structure. Instead of a steel frame bolted to the seafloor, a Condeep was a massive concrete gravity base, a cluster of hollow cylindrical cells that sat on the bottom under their own weight. So you'd build the cells in a dry dock, tow the structure out to sea, and slowly flood the chambers to sink it onto the seafloor, exactly where you needed it. Sleipner A was the 12th Condeep platform ever built. It was designed to sit in 82 meters of water in the Norwegian North Sea and extract gas from the Sleipner field, one of the largest gas deposits in Europe. The gas it would produce was tied to a supply contract worth billions, covering up to 10% of Western Europe's total gas demand for 30 years. The pressure to deliver on time was enormous. The structure itself was extraordinary. 110 meters tall, 24 concrete cells, each 12 meters in diameter. 4 of those cells extended upward into shafts that would hold the platform deck. And it had been designed using the most advanced structural analysis software available. Programs that could check thousands of locations on the structure against hundreds of different load scenarios. The engineers were confident. The math had been done. The structure would work. There was one problem. The math was wrong. Here's where things get technical. But stay with me, because the detail matters. Where Sleipner A's cylindrical cells met each other, there was a structural element called a tristle. Picture the gap between 3 circles pressed together. That triangular space in the middle. In a concrete structure, that junction has to carry an enormous amount of force. As the platform descended deeper into water, the pressure on those walls would increase dramatically. And the designers used a program called Nastran, one of the most widely used finite element analysis tools in the world, to calculate exactly how much stress those tricell walls would experience. Finite element analysis works by breaking a complex structure into thousands of tiny pieces and calculating the forces on each piece. It's incredibly powerful, but it's only as good as the model you build inside it. And the model for Sleipner A had a flaw. The mesh, the grid of calculation points used to model the tricell, was too coarse in a specific, critical zone. The software was making approximations where it needed precision, and those approximations led it to underestimate the shear stress on the tricell walls. Not by a little, by 47%. Let that sink in. The walls that were supposed to hold back the pressure of the North Sea were designed to handle roughly half the force they would actually experience. The concrete walls in that zone were built too thin. The reinforcement was insufficient, and nobody caught it, because the software said everything was fine. 3 years of construction, thousands of engineering hours, millions of dollars, and a critical number was off by nearly half. The morning of August 23rd was not an unusual day for the Sleipner project. The hull had been built and was being prepared for deck mating, the process of attaching the platform's upper structure to the concrete base below. To do this, engineers needed to carefully lower the concrete hull deeper into the water. They had a precisely controlled rate of 1 meter every 20 minutes. This was normal procedure. Every Condeep before it had gone through the same process. There were 14 people on board. As the hull descended past 65 meters, an engineer heard something unusual. A deep rumble, then another. Then the sound of water. Not from outside the structure, but from inside it. A wall in one of the tricelles had failed. A crack had opened, and the North Sea was pouring in faster than any pump could handle. The crew had minutes. They abandoned ship. From the surface, those who watched described the platform lurching, then tilting, then disappearing beneath the water at terrifying speed. As it sank into the 220-meter fjord, the pressure became catastrophic. The hollow concrete chambers, the very cells that were supposed to provide buoyancy, imploded as the water pressure overwhelmed them. Each implosion sent a pulse of force downward. When the debris hit the floor of the fjord, seismographs recorded a 3.0 magnitude earthquake. All 14 crew members survived. They were rescued by nearby boats within minutes. The structure was gone. 2 years of planned gas production, gone. And Statoil, the Norwegian oil company that owned the platform, was now facing a $700 million loss and the task of figuring out exactly what had happened. Statoil brought in SINTEF, Norway's largest independent research organization, to lead the technical investigation. What they found would become one of the most studied cases in structural engineering history. The investigation confirmed what the eyewitnesses had reported. A tricell wall had failed first. The crack propagated rapidly, and the platform was lost within minutes of the initial failure. But why had that wall failed? The investigation team went back to the original computer models. They reran the analysis using more refined mesh parameters, more calculation points, tighter approximations. And when they did, the answer became clear. The original Nastran model had been built with a mesh too coarse to accurately capture the shear forces at the tricell junction. The software had returned results that looked reasonable, but they were wrong, and the actual stress on those walls was 47% higher than the model predicted, far beyond what the concrete could withstand at that depth. The walls had been designed exactly as the software specified, built exactly to specification, inspected, approved, certified, and they were never strong enough to survive the conditions they were designed for. The investigation also found that the Norwegian concrete codes used at the time were unconservative, meaning they allowed engineers to rely on calculations that didn't include enough safety margin for structures like this. When it came time to build the replacement platform, the engineers made a striking decision. They were so uncertain about the new computer software that they chose not to use it for the critical structural design. Instead, they went back to pre-computer methods, slide rules, hand calculations, the same techniques used on the earliest Condeep platforms 20 years before. The replacement platform was completed in 1993. It has operated without incident ever since. The story of Sleipner A is not really about concrete. It's not even really about software. It's about the gap between confidence and certainty. The engineers who designed Sleipner A were not careless. They used state-of-the-art tools. They followed approved standards. They checked their work against accepted codes. By every measure they had available, the structure was sound. And the problem was that their measure was flawed, and nobody had a reason to question it. The software said the numbers were good. The inspection confirmed the build matched the design. The certification process checked the boxes. What nobody checked was whether the model itself was accurate enough to trust. This is a failure mode that engineers still wrestle with today. The more powerful our tools become, the more we tend to trust their output without questioning their assumptions. A more precise-looking answer is not necessarily a more accurate one. The Sleipner investigation led to significant changes in how finite element analysis is validated in structural engineering, particularly for offshore structures. New guidelines required engineers to verify that their mesh was fine enough in critical zones to produce reliable results. But the deeper lesson is harder to encode in a guideline. Sometimes the most dangerous thing in engineering isn't a bold mistake. It's a quiet one, a number that looks right, in a report that looks thorough, approved by people who had every reason to believe it. A 40,000-ton structure sank to the bottom of a Norwegian fjord because a grid of calculation points was slightly too sparse in one triangular junction. And nobody knew until the water started coming in. If you found this story worth knowing, there are hundreds more like it. Engineering decisions that seemed reasonable at the time and catastrophic in hindsight. That's what this channel is about. Next video, a Soviet military officer receives a warning that 5 American nuclear missiles are headed toward Moscow. He has 4 minutes to decide whether to report it as a real attack or call it a false alarm. One man, 4 minutes. The fate of the world. Subscribe so you don't miss it.